Hello everyone, my name is Aditya Sharma and this is Fundamentals of Compressible Flow course being conducted by Department of Mechanical Engineering IIT Guwahati under the NPTEL program. And it's a 12-week course and we are into 10th week of this course. So regarding this week 10, we are conducting this tutorial session. So the topic that we will be covering in this week's content is compressible flow with friction and heat transfer. So with friction and heat, what happens to the compressible flow? Instructor for the course is Professor Niranjan Sahu, again from Department of Mechanical Engineering, IIT Guwahati, and I am a research scholar here at Department of Mechanical. So we shall wait for a few minutes to see if somebody joins. After that, we can continue with the session. Thank you. Okay, so we can start with the session. Compressible flow with friction and heat transfer. So in total, there are three lectures in this week's content. Lecture number 23, lecture number 24, and lecture number 25. So in lecture number 23, you have related to heat addition in your compressible flow. Then in your lecture 24, you have related to your friction, effect of friction on compressible flows. Then in lecture number 25, you see two curves. One is Rayleigh curve and one is Fano curve. So Rayleigh curve is related to heat addition and Fano curve is related to your frictional effects in compressible flow. So majorly, this has been covered. So we'll start with lecture number 23. Its topics and questions, and the same way we'll see then lecture number 24 and lecture number 25. So first topic here is compressible flow in one-dimensional medium. So this topic basically is the revision of your whatever you have studied in previous lectures related to your one-dimensional compressible flow. Okay, so this is that, right? So how across your shock properties change, right? So as we know that across your shock, your static properties, your pressure, temperature, density, they increase, right? And your if you talk about your Mach or velocity, it decreases across your shock. And then there are pressure losses also, total pressure losses, okay? Loss in your total pressure, but your temperature remains same. Also, there is increase in entropy across your normal shock. Okay. So all this has been taken care in this topic. Then one-dimensional flow with heat addition. Okay. So here the assumptions that have been discussed are, or the assumptions that have been mentioned are the flow occurs in a constant area duct. So it talks about the discussion talks about a constant area duct. Okay. And the flow is considered as steady for calorically perfect gas. So this is second assumption. And then there is another assumption that there is no work interaction. There are no body forces. There are no frictional effects. Okay. So this is there. Then fundamental equations of 1D flow have been discussed, right? So continuity equation, momentum equation, and your energy equation. So these have been discussed. Okay. Fundamental equations have been discussed, right? So this is rho1 u1 equals to rho2 u2. One is this. Second is p1 plus rho1 u1 square is equal to p2 plus rho2 u2 square. So this is your momentum equation. Then your energy equation is h1 plus u1 square by 2 plus q is equal to h2 plus u2 square by 2. So this is your energy equation. Okay. So this is there. So next topic is flow property calculation with heat addition or rejection expression for static property ratios, upstream, downstream of flow, expression for static total pressure and temperature ratio, upstream, downstream of flow. So then there are expressions for these topics. Okay. For this, you can refer to your lecture 23. Okay. Slide number 8, 9, 10. Right. Then there is thermal choking. So choking, uh, we know what is choking, right? So in your CD nozzle, you have seen that at the throat, you were getting sonic flow. Okay. When the pressure ratios, appropriate pressure ratio of your inlet and your exit was maintained. So you were getting sonic flow at your throat. Okay. And in that condition, you're calling it choke because beyond this choked uh, state, uh, the mass flow rate cannot further increase. That's why choked. Okay. So this was your in your CD nozzle. So same way here, this choking refers to your sonic state. Okay. And the sonic state that we are achieving in the flow in a constant area duct that we are doing with the help of sorry so that we are doing with the help of heat. So that is the only difference. Okay. So this is there. Then moving on to questions. First question is there. So it says that within the thin shock region, flow field is considered isentropic. So this is a false statement. Okay. Within your shock region, okay, it's a very thin region of the order of 10 raised to the minus 7 meters. So there, if we talk about the entropy, so this is isentropic region. Okay. So this you can find in your lecture number 23. The next question is this. Mostly in this session, we have statements type of questions where we have to tell whether the statement is true or false. So at times it can be confusing that whether a statement is correct or not. So we shall see one by one. Whether the statement is correct or not. So this question here says that when the frictional effects are taken into consideration, the flow field can be considered isentropic. So if your frictional effects are there in the flow, so can you call your flow field to be isentropic? So if you have gone through the lecture, you should be able to answer this question. This way we will be able to revise the content of our lectures. So when the frictional effects are taken into consideration, the flow field can be considered isentropic. So whether this is a true statement or false statement. So this is a false statement. Okay. So the entropy does not remain same when your frictional effects are taken into consideration. Right? So this was your question number 2. So third question, please read the question and try to give an answer. Try to see if this is statement is correct or not. So it says that combustion in a ramjet engine is an example of heat addition in a compressible flow. So this is a correct statement. Okay. So two examples have been given. One was given of your a wind tunnel. Okay. Where through lasers heat is added. And then this example of combustion in a ramjet engine has been given in your lecture number 23. Okay. So this is a true statement. Then moving on to next question. Please read the question and try to give an answer. The question here says that which of the following statements is not an assumption for a one-dimensional flow with heat addition. So this is the question. Please try to give an answer to this question. So the first option says that the flow occurs in a constant area duct. Okay. Then the flow is considered as steady for an ideal gas. There is no work interaction. The frictional effects are negligible. So here if you see, first statement is there in the assumptions. Now about second option, we are not sure. Fourth option is there. Third option is there and fourth option is there. Now in your second option, what is the difference? So the flow is considered steady for an, here it is written for an ideal gas, but for assumptions, we take a calorically perfect gas. Okay. Minor differences are there between these two. Okay. So your for your calorically perfect gas, your constants, heat constants. Okay. So they are independent of temperature, but in your ideal gas, it can be dependent and it can be independent. Okay. Both can be there. So the assumption is for calorically perfect gas only. So in that case, which is not an assumption, so B is the right answer to this question. So question number 4. Then moving on to next question. please read the question. So question number 5 here says that air is entering in a heated duct at Mach 2.3 with atmospheric pressure and 293 Kelvin. So temperature, the static temperature has been given. Some mistake in language. Okay. 293 has been given as your static temperature. Neglect the frictional effect. Calculate the amount of heat required to choke the flow at the exit of the duct if the stagnation temperature at the downstream becomes 1.3 times the upstream. So you have a duct, okay? Mach entering with Mach 2.3. Then T here is 293 Kelvin. Now you want it to be choked at the exit. You want that your this gets choked. Okay. Now here you have some total temperature. Here you have some total temperature. And your this is 1.3. This question asks the amount of heat added to choke the flow. So the amount of heat added will be calculated the amount of heat added will be calculated as your Cp. Okay, your specific heat at constant pressure. So this. Now T naught here is not given, so we need to find out T naught. Cp is given, T naught star also we do not have. But because we have this ratio, so once we have T naught, we can find out your T naught star. So first using isentropic relation, we will find out T naught. Yes. So T naught by T is equal to 1 plus gamma minus 1 by 2 m square. So this is there. So this is equal to 1 plus 1.4 minus 1 by 2 1 plus 0.2, okay, into 2.3 square. So now calculate this. So this comes out to be this. Now T we have in the question, which is 293 Kelvin. Okay. So calculating this, we get this. Now this is there. Calculate this. So this is there. Hence, Q is equal to Cp is 1.005. If you see the question, 1.005 kilojoule per kg Kelvin. Calculate this. So this is there 181.80 kilojoule per kg. Within the range. Question number 5 this was. Then we will move on to next lecture. Sorry. So lecture number 24, compressible flow with friction and heat transfer. Concept of friction in circular pipe. So in this topic, so this talks about your pressure heads. Okay. because of your friction, okay, your because of your wall shear. So how the flow encounters head losses. So this has been discussed in this topic. So this has been shown this way. This has been shown by means of a pipe, tilted pipe. Okay. So this pipe has some length L and it has some radius R. And from the ground, this is delta Z. Okay. Then it talks about your head losses. Okay. So this is your delta Z is your gravitational head, and this is your delta P by rho G is your pressure head. Okay. So delta P is related to pressure at your entry and exit, and delta Z is related to your uh, gravity, because of gravity, the head you that have, or potential energy, you can say. So this is related to your wall shear stress by this formula. So this tau with subscript W is your wall shear stress. So this has been given in your lecture number 24. The basic idea here is that uh, in your friction when comes into picture in your compressible flows, the basic idea is that you can change the flow properties by changing the length of your duct. Okay. So be it your subsonic flow, be it your supersonic flow, if you change the length of the duct, it is going to change the flow properties. Okay. Because you're by increasing the length, basically you're increasing the frictional effects. So that is the whole idea, right? Then your flow properties related to your frictional effects. So this has been discussed in your slide 9 of your lecture number 24. Okay. Now from your like there was thermal choking, so same way you have frictional choking. Okay. Because of friction, now your flow is getting choked. And from here you have one formula. which is so this is there. Now here, this is average friction coefficient. D is diameter of cylindrical control volume. Okay. M is for your mag. Yes, gamma is ratio of specific heats. So this is there. Now L star is the length for which your flow will choke. Okay. So this is there. So initially you have flow with mag M. Okay. And then diameter is D of the cylindrical control volume that you are considering. And the frictional effects have been taken into consideration using F bar. Okay. In that condition, what length is going to give choking? So this can be, sorry, this can be calculated using this formula. Right. So this is there. Then let's see the questions. So this is related to frictional choking only. This question is there. Question number 6. So question number 6 there says that in case of flow in circular pipe, shear stress can be related to geometric parameters of the pipe only when flow is laminar. So whether this is true statement or false statement. So this statement basically is very strict statement, okay, which says that only geometric parameter of the pipe only can be related to your shear stress when your flow is laminar. So this is not true because your flow properties also you can relate to your shear stress. Okay, so this is a false statement. Your flow properties and your fluid properties you can relate to your shear stress, right? So in that case, this is a false statement. To consider the frictional effects in a compressible flow, it is modeled as a shear stress at the wall. So this is correct. Okay. Then next question is, so this is there. Question number 8. So on frictional effects. So it says that air with gamma equals to 1.4 enters through a 145 diameter pipe with inlet Mach number of 2.3, for which the non-dimensional parameters is equal to 0.3478. So this is there. The average value of friction is 0.004. The length of the duct in meters required to choke the flow at the exit of the duct is. So this question is there. So this is there, implies L star is equal to 0.3478 into D divided by 4F star. So this comes out to be this 3.15 meters. This is the answer to your question number 8. Okay, which is within the range that has been provided to us. And moving ahead. So next lecture, last lecture, lecture number 25. So before starting this, we can take a short break of 5 minutes, 5 to 10 minutes. After that, we can continue with the session. Thank you. So we can continue with the session. So last lecture of the session topics. So here a Rayleigh curve has been discussed. Then Fano curve here has been discussed. So initially introduction to compressible flow has been given, then across the normal shock, how the properties behave, flow properties behave, this has been given. Then one-dimensional compressible flow with heat addition. So this has been given. So these two curves, Rayleigh curve and Fano curve, are sufficient enough to understand the heating effects and the frictional effects respectively. Okay, so first we will see the Rayleigh curve. Also in your heat addition, so if you talk about your total pressure, so this total pressure decreases on heat addition and your total temperature increases. So this we have seen in the numerical also. If you see this numerical, so total temperature T naught star, if you see, so this had increased to 783.89 Kelvin from 602.994 Kelvin. Okay, so your total temperature has increased or increases in this case. Then looking at the Rayleigh curve. So there are 2 points B and A. Okay, so it's a Mollier diagram basically. So this curve has two halves. One is the upper half and one is the lower half, which are divided by point A. Okay. Then there is point B also. So your point A is your of maximum entropy sonic state. So this is your sonic state, which has maximum entropy. And point B is of maximum enthalpy. So this is there. Then if you see the upper half of the curve, so this curve belongs to your subsonic flows. Okay. So let's say you have some subsonic flow with some Mach. So you increase. Initially, let's say this is your position. Okay. C. I'll call it C. Then you add heat to this. Okay. So this curve is going to move towards point B or point A. Okay. And as you keep on increasing the heat in this initial state, this will further move towards point A. And a point will come where the enthalpy of this flow will be maximum. Okay. But then beyond this point, its enthalpy cannot increase. Why so? Because its kinetic energy also has increased substantially. So previously till point B, what was happening was that your heat addition rate was greater in comparison to your flow velocity. Okay, so your enthalpy was increasing, but beyond point B, that is not the case, and hence your enthalpy further does not increase. And eventually, you get sonic state at your maximum entropy A. Okay. Now, if you see the lower curve, lower portion of the curve, so that corresponds to supersonic flow. Okay. So I could have called it B dash. And this point I'll call as A dash. So if now I have a flow with supersonic flow properties, okay, this location of its enthalpy and entropy is A dash. Now if we add heat to this flow, so this will further go towards point A, sonic state. Okay. Then you further increase the heat, it will reach sonic state, right? Now, regarding cooling, what are the effects? Or heat rejection, what are the effects? So if you see the subsonic curve, so with heat addition, it was moving towards A from B dash. Now it has reached, now if you decrease the heat or reject the heat from the flow, so it will move in opposite direction. Okay, obviously. But if this flow has reached to point A with where it has maximum entropy, so theoretically you can further expand it or increase its Mach, okay, and make it further supersonic. So how you can do that? By cooling, okay, because at this sonic state, if you cool, if you see the lower curve, on cooling, this moves towards from A to A dash. So now from subsonic state, your flow has reached to point A because of heating. Now, if you cool this flow, it will start moving towards A dash. So this is there. And opposite is the case with the supersonic flow, okay, in terms of direction, okay. So from A dash to A, it will move with heating, okay. So its Mach is going to decrease with increase in heat or with addition of heat. And once it has reached the sonic state, if you uh, now cool this reject heat from this flow, so it will become subsonic. So this is there in Rayleigh curve. Right. Now about your sonic state, let's say your flow is at sonic state from subsonic flow because of heat addition. Now at this sonic state, if you further add heat here, okay, at this point A, if you further add heat, then this is going to give you normal shock, right? Then we'll see the Fano curve. So Fano curve corresponds to frictional effects. Again, it's a Mollier diagram between enthalpy and entropy. So this is there. So this is your sonic state. Let's call this A again. So what happens with increase in length of the duct in which the flow is taking place? So for your subsonic flow, so the upper portion of the curve is for subsonic conditions, and the lower portion of the curve is for your supersonic conditions. So at your subsonic conditions, if you are going to increase the length of your duct, then because of frictional effects, your flow will, the Mach of flow is going to increase. And if you keep on increasing the length, uh, A point will come where the flow is going to get choked. That is point A. Okay. Which we call as L star also. And when your flow is supersonic, you keep on increasing the length of the duct, its Mach is going to decrease. And same is the case here also, that for a critical length, your flow is going to get choked. Okay, your Mach is going to become 1. And now, what is the effect of friction on your pressure? So your total pressure decreases for both the cases. Be your flow subsonic, be it subsonic, be it supersonic, your total pressure is going to decrease. So this is there. So if you see the lecture number 25, in slide number 24, one statement is there. So it says that it is impossible to first slow a supersonic flow to a sonic condition and then further slow it down to subsonic speeds by friction. This deceleration of subsonic flow by friction would violate second law of thermodynamics. Okay, I hope this is understood. First, let's say we are going to this move the flow from supersonic to sonic state. Now, from sonic to further, we want to change it to subsonic state by means of friction only. This we cannot do. Okay. Maybe by cooling we can do, but from friction this is not possible. Okay. So this is low. Then we'll move on to questions. So question 9, it says that when heat is added to a compressible flow, its Mach number increases. When heat is added, its Mach number increases. So let's go to the Rayleigh curve. What it talks about heat addition. So if you see the Rayleigh curve on heat addition, your Mach increases. Is it the case? So for subsonic, you see your Mach is going to increase, but for your supersonic, no. On heat addition, your Mach is decreasing. Okay. So when it says that your Mach increases, so we cannot say it's going to increase or decrease. You'll have to tell what is the initial Mach that we have. So we cannot say. Okay. So this question here says that what happens to the static pressure of supersonic flow when heat is added to it? When heat is added, what happens? Please see this question. So supersonic flow is there. Your velocity is going to, with heat addition, your velocity is going to decrease and your pressure is going to increase. Static pressure is going to increase. Okay. So A is the correct answer to this question. Then question number 11 says that heat rejection always drives the Mach number towards sonic state, either by decelerating a supersonic flow or accelerating a subsonic flow. So heat rejection always drives the Mach number towards the sonic state. So this is not heat rejection, this is heat addition. So if you see your, it's a false statement, right? If you see your Rayleigh curve, heat addition is moving the flow to sonic state. Maximum enthalpy state in Rayleigh curve corresponds to sonic state. Maximum enthalpy state is B. Does it correspond to sonic state? No. That is maximum entropy. Okay. In that case, this is a false statement. Then the upper branch of Rayleigh curve corresponds to supersonic flow and the lower branch of Rayleigh curve corresponds to subsonic. Lower branch corresponds to supersonic. Okay, lower branch, if you see, this corresponds to supersonic and upper branch corresponds to subsonic. What happens to Mach number of supersonic flow in a duct with friction? So your Mach number decreases. We have seen in the Fano curve, as we keep on increasing the length of the duct, its friction is going to increase. Frictional effects are going to increase, which eventually will decrease the Mach number. The upper half of Fano curve corresponds to subsonic flow, while the lower one is meant for supersonic flow. Upper half is for Fano subsonic and lower is meant for supersonic. That is true. Okay. You can see the curve. A supersonic flow is compressed with increase in friction. Compressed means your static pressure is increasing. So with friction, static pressure increase. So if you see your Mach is decreasing, okay, and your static pressure is increasing. So this is a true statement. I hope this is clear. Then next question is there. It says that for a subsonic flow, increase in length of the duct causes the static pressure and enthalpy to drop, but the flow velocity and entropy increases. So for a subsonic flow will increase in length of duct because of frictional effects. Your back is going to increase, or velocity is going to increase, your entropy is going to increase. Okay. But if you see the Fano curve, what does it say about your enthalpy? It says that enthalpy is dipping. Okay. It is dipping downwards. So there will be a drop in enthalpy, and static pressure is also going to drop. Okay. So this is no statement. So this question here says that friction always causes the drop in total pressure is irrespective of inlet flow Mach number. Eighteenth question. So it's raining very heavily here in Guwahati. Question number 18. Friction always causes the drop in total pressure, irrespective of inlet flow Mach number, supersonic or subsonic. So this is the true statement. Okay. There will be loss in total pressure. Question number 18 is correct. So this is it about today's session. So I'll conclude the session. So there were three lectures. Lecture number 23 to lecture number 25. In lecture number 23, we saw heat effects, heat addition in your compressible flow. Okay. Where we started with 1D flow with heat addition. Okay, with basics we started, and then 1D flow with heat addition. So this was there. So here it says that heat addition is the driving force for change in entropy. Okay. Then there were flow properties, how we can calculate flow properties in case we have heat addition and compressible flows. So expressions are there. So you can go through the lecture number 23. Link will be in the description. Then concept of thermal choking. So because of heat, you can attain M equals to 1. Then in lecture number 24, we saw frictional effects. Okay. In a circular pipe, we started with the head losses. Okay. gravity and pressure had losses we started with. Then we saw fundamental equations for friction, for study of friction in compressible flows. Then we saw an expression for L star, critical length of your duct for which your flow will get choked because of your friction. This we saw. Then lecture number 25 basically is the crux of both the lecture number 24 and lecture number 23 and lecture number 24. Okay. So where we saw inferences from heat addition. Okay. So how the pressure behaves, static pressure behaves, how the total pressure behaves, what happens to temperature. So all this has been discussed here. Then we saw Rayleigh curve and Fano curve. So Rayleigh curve is related to your heat addition and Fano curve is related to your friction. So this is it about heat addition and frictional effects in compressible flows. Okay. Right. So this is it about today's session, uh, session number 10. So now we are left with two more sessions and one extra session. So if we see the dates, on 7th and 7th of April and 14th of April, we have two sessions scheduled. But I'll also take one more session on 11th. That is Saturday, 11th of April. I'll taking one more session. So my 11th session will act as the session on 11th of April will act as the 12th session, session corresponding to week number 12. And in the session that is scheduled on 14th of April, so we will be concluding the whole subject. Okay, the whole course we will be concluding, and broadly we'll try to revise the topics that have been covered in the whole course. Okay, so thank you. Thanks for watching this session. The next session will be on coming Tuesday only. Thank you.